Hi guys, today we're going to be talking about exponential models for growth and decay. Let's refresh our memories about our exponential function to start. So we started working with these a little bit the other day. The general formula is y equals a times b to the x. Do you remember what a stood for? So a stood for the initial value. The b value, when it was greater than 1, so if it's greater than 1, it stood for the growth. And if it was a fraction or between 0 and 1, it stood for decay. So today we're going to start playing with some of these and graphing them and talking about how to do it. So another way of thinking about this is y equals our initial value times 1 plus the rate, all raised to some sort of time. So let's see what these start talking about. A population of fruit flies is growing, so it's got to be greater than 100 at a rate of 6% per hour. The population starts at time 0 with 28 flies. So let's talk about what we know. So we know our A value. How many flies did we start with initially? 28. Good. B, because it's growth, is 1 plus the rate. So 1 plus 0.06, 6% as a decimal, is 0.06 equals 1.06. So now I know it says that we want it as a P for the population, T for the time. So Y is equal to P and X is equal to T. So we have P equals 28 times 1.06 to the T power, if I put that all together. Find the value of P of 24. P of 24 means replace T with 24. So we're doing 28 times 1.06 to the 24th power. You're going to type that into your calculator. We're going to get 113.37. What does the calculation you made in C represent about the fly population? So this means after, what are we measuring in? T is hours. After 24 hours, the fly population after 24 hours, the fly population, oh, these little buggers, they got so many, is 113. Imagine going to bed with 28 flies and waking up at 113. Awesome. What is the range? So the range, where did we begin? Where did we end? We began with 28 flies. We ended with 113. Good. So we're going to do a sketch of this. We don't really need to know this quite as well as how we used to because we're not really going to be taking a Regents exam. So just know if you type this into your calculator, actually we'll just skip this. We don't have to do that. We'd have to monkey with our window and do that kind of stuff. I'd rather you just know what you're doing. Exercise 2. In a savings bank account, if the savings in a bank account can be modeled by the function S of t equals 250 times 1.05 to the t, which of the following can be true? So let's just take our initial formula, y equals a times b to the x. A stood for the initial value. So how much money did they begin with? $250. So they have S of t equals 250 times 1.045 to the t. we know that B equals 1 plus the rate as a decimal. So they're saying it's 1.045. So our R is 0.045 as a decimal. So in terms of a percent, we move that over and we get 4.5%. So we're looking for an initial value of 250, a rate of 4.5%. So that would be choice 3. In exercise 3, they have water draining out of a pipe. Water drains are out of a pool, excuse me. The depth of the water decreases. So once I see decreases, I know B equals 1 minus the rate at a constant rate of 20% per hour. The depth of the water when draining begins. So begins is A equals 12 feet. Based on the information below, or above, sorry, create an equation that gives depth D of the water in the pool as a function of time in hours it has been draining T. So let's take our general equation. Y equals A times B to the X. A equals the initial, which is 12 feet. B is 1 minus the rate because it's decreasing. 1 minus 20% as a decimal is 0.2, so that's 0.8. X is equal to time, Y is equal to D. So D equals, our initial was 12 times 0.8 to the T. We did it. For part C, it says, it's safe to cover the pool after it reaches a depth of 1 foot or less. What is the minimum number of pool hours we should rate to cover the pool? So if I was doing this, I would type this into my Y equals 12 times 0.8 to the T. We would go and read our table. So we're looking at for when our output, our depth has to be less than 1, less than or equal to 1. So type this into your Y equals. We'll copy down our chart. So at 9 hours, 10 hours, 11, 12. At 9, I have 1.6 on my table. At 10, I have approximately 1.3, so we're not there yet. At 11, I have 1.03, and at 12, I have 0.82. So what is the minimum number of whole hours? So it's going to take us at least, so it's going to take us 12 hours, because at 11, I'm not quite there yet. There's still a little bit left. And then you could say, how did you find your answer? Used the calculator. For exercise 4, which of the following equations would model an exponential quantity that begins at a level of 16 and decreases at a rate of 8%? So Y equals A times B to the X. Our initial value says begins at 16. B decreases. So B is 1 minus the rate. 8% as a decimal is 1 minus 0.08, which is 0.92. So I'm looking for 16 times 0.92 to the T. So choice 1. Exercise 5. Aaron takes a loan from a bank for $1,000. The bank, so that's our initial, bank charges him 2.5% interest compounded annually. Write the amount of money Aaron will owe the bank after 2 years. So we know the initial value is 1,000 as he increasing or decreasing the amount he owes? So it's increasing because of the interest that he has to pay. So 1 plus the rate is 1.025. Y equals M of t, X equals t. So we're plugging into this. Y we said was M of t equals 1,000. 1 plus the rate is 1.025 to the t power. How much will Aaron owe after 6 years? So years is our time, so t equals 6. Please plug in 1,000 times 1.025 to the 6. So $1,159. Watch your rounding on the change, 69 cents. Aaron's parents said they would help him pay back the loan as long as it does not exceed $1,500. What is the maximum number of whole years Aaron can wait before paying back the loan with his parents' help? Explain. So again, I would go to my graphing calculator. I would type in 1,000 times 1.025 to the t power, or x. Yeah, put an x in the calculator. We're looking for where the graph, the last time it's less than 1,500. So type it in your y equals. Let's copy down the table. So we have t, and then we have m of t. So at 15, I have 1,448. At 16, I have 1,484. And at 17, I have 1,521. So this is the last time that it's under 1,500. So Aaron can wait 16 years. That's a long time. All right, there's some practice for you to get used to answering the questions with the initial value and the rates. At the bottom here, these are some really good questions. We'll go through them. So if you're working on them in class, that's awesome. So number 7, I'll take that one out. That one was tricky, but the rest of them are pretty darn good. So good luck. Ask for help if you need it. And have an awesome day.